All right. Part D of Module 3, Fibonacci formula and linear recurrence relations. Two topics in this part. First, we need to prove Fibonacci formula. Second, we need to learn how to solve linear recurrence relations. D.1, verify Fibonacci formula only for special cases. Because for the general case, it is too hard. So you cannot verify directly. So you have to find some special way to prove it. All right, so let's start. Verify the Fibonacci formula. Let's start from the first initial value where n equals 0. All right, so when we move to the general case, we need to use the powerful tool, mathematical induction. We use it in our binary bits problem. Here, let us use another time. It is not very easy, so we need to do a lot of work. But let us start with the easiest case. First one, F0, you plug in n equals 0 in the general formula, where n equal to 0. Pretty trivial, Phi to the 0, 1, 1 over 1, 1 minus 1, 0. So the answer is 0. F1, so you plug in 1, okay? Then we need to use that 1 plus root 5 over 2 definition of the golden ratio. But here, this number not very convenient because 1 plus root 5 is at a denominator. So we want to change its form. So we want to make a more friendly form. So that is this one. Can you see it? How to get that? It's pretty easy. The standard way we use to make this change, we multiply the conjugate of this number, 1 minus root 5, 1 minus root 5, right? But when we simplify it, 1 minus 5, remember? A squared minus b squared. Here we use the formula a squared minus b squared equals a plus b times a minus b. Okay? A plus b, a minus b. A plus b, a minus b equals a squared minus b squared. Okay? So then, numerator 1 minus root 5, but this is negative 4. After simplification, we get this number. Because we need to change the sign. So we switch root 5 and 1, the position, changing the sign. All right, so after that change, we can easily find the value. Same denominator, numerator 1 minus 1 cancel out. 2 root 5, 2 cancel out. Root 5 cancel out. So 1 answer. F of 2, you can see a little harder because we need to take square. The second term square, we use that, root 5 minus 1 over 2, that expression. Then we use the a plus b parenthesis square formula. A minus b parenthesis square formula. We use that. Then 5 cancel out, 1 cancel out, 2 root 5, minus negative, minus plus, right? Yeah. So we get a 4 root 5. 4 cancel out. Root 5 cancel out. Answer is still 1. Okay? So you can see our verification for the first 3 cases correct. If we just need to apply mathematical induction, that's already enough. We already have, actually F2 not necessary to apply mathematical induction. We only need to verify F0, F1. Yeah. But the reason I calculate F2, just show you how to do, a little more verification. Now, we can look at F3 because this one is much harder. Now, too hard to calculate for most of you, probably. All right. But here I like to show you another example. Yeah. So let's verify one more case. Yeah. Here, to do this calculation, we need to use some special trick here. Yeah. So what's that? The reason the degree is too high, right? Too high, so we like to bring it down, right? Yeah, by our intuition, because if the degree is too high, from natural thinking, we should bring down the degree by formula transformation. So the strategy, let's set our strategy. Strategy, reduce the degree to make the calculation easier. But the question, how to reduce the degree of phi cube transformation? All right, we need to do the work here, transformation work. Phi cube, we split this expression into 2 operands of multiplication, phi times phi squared. Phi squared. Transformation. Then let's use some special property of phi. We know phi is a root of this quadratic equation, x squared minus x minus 1. So when we plug in phi, we get phi squared minus phi minus 1 equals 0. And we can rewrite this equation as phi squared equals phi plus 1. Okay? So that is our first property. But we can also write 1 equals phi squared minus phi, the second property. Okay? So these 2 properties very useful when we do formula transform. Sometimes we use the first one, sometimes we use the second one. Okay? Here, let me show you how to use these 2 properties. All right. Here, we replace phi squared by phi plus 1. So we use the second property. Okay? Then multiply through, so phi squared plus phi, this phi squared, we can replace it by another phi plus 1. So then plus phi, we get 2 phi plus 1. In this way, you can see we bring down the degree of the expression from 3 to 1. From 3 here, 1. All right? From 3 to 1. Much simpler. Let's work on 1 over phi cubed. This time, we use the first property. We replace 1 by phi squared minus phi. Why we do that? So here it looks like we increase the degree, right? Phi 1, you have 0 degree, right? Phi to the 0. But now we replace it by phi squared minus phi. We increase the degree of the polynomial to 2, right? It looks more complicated. There is some good reason, because after we increase the degree, we can do cancellation between numerator and the denominator. After the cancellation, the degree of the denominator is brought down. Yeah. So that's what we need. After cancellation, phi minus 1 over phi squared. All right, but we want to bring down phi squared another time. So we replace this one by another parenthesis, phi squared minus phi. After simplification, we get 2 phi minus phi squared. After that, you can see we have common factor between numerator and the denominator again. So we can do another round cancellation, phi cancellation. Okay. After that, we get 2 over phi minus 1. That's simple enough, right? So we do not need to do further simplification, although probably we can, right? If you like, you can do further cancellation, right? Yeah. Do you want to do it? Yeah. So we can do it. Yeah. If we like, 2 times phi squared minus phi over phi, another round cancellation, 2 times phi minus 1, right? Yeah. Okay, yeah. So you can do another round factorization, right? Yeah, all right. But do we need that? Yeah. Sometimes it may not be good, right? Although we can, but it may not be the best way, right? Yeah. So you can think about it. Yeah. All right. But here we do not do further transform. Yeah. So we stop somewhere. All right. So now let us evaluate phi cubed plus 1 over phi cubed. Yeah. With our new expression, because plus 1 minus 1 cancel out, we take that 2 out, so we get this new expression. This tells us phi 3 equals 2 phi 1. Yeah, because left-hand side, if we multiply root 5, and the right-hand side, we also multiply root 5, left-hand side, we get phi 3, right-hand side, we get 2 phi 1, right? Now, so we get it. Phi 3 equals 2 phi 1, that is 2. So you can see another verification like this. Yeah. But you can see we need to do a lot of transformation using the properties, 2 properties of phi. Okay, yeah. All right. So now we have enough practice. Here, I try to give you a little more chance to do the practice. Yeah. Now we are ready to complete mathematical induction, the main step. But I leave that main step to our video D.2. Yeah. All right, so let's stop here for our D.1.